In this video, we look at the calculation of gears with involute teeth in order to determine the listed parameters mathematically. For the calculation, the involute tooth must first be described mathematically. As already explained in the video on the geometry of involute gears, an involute is created by rolling a straight line on a base circle. The illustration shows the involute to the base circle with a radius RB. A point P on this involute can be clearly described by the angle alpha shown. This involute angle is the angle between the straight line GP and the straight line GT. The point G corresponds to the center of the base circle and T to the tangent point on the base circle. The length of the distance TP corresponds to the radius of curvature of the involute at point P. Furthermore, the distance TP corresponds to the circular distance on the base circle SD, since in the involute construction the rolling straight line rolls on the base circle without sliding. Therefore, the given relationship applies. However, the point P on the involute can be described not only by the angle alpha, but also by the angle phi. This is the angle between the straight line GP and the straight line GS, where S corresponds to the point of the involute on the base circle. Both angles are obviously clearly related. This relationship can be derived relatively easily using the equation given. If we use radians to specify the angles, the circular distance SD results from the product of the base circle radius and the sum of the angles phi and alpha. The distance TP can be determined from the base circle radius and the tangent of the angle alpha. This means that the stated relationship between the angle phi and the angle alpha applies. This relationship between the two angles is also known as the involute function. Note that all angles in this function must always be given in the unit radians. This involute function is used to determine many geometric parameters of gears, as we will see later. The reason for using the angle alpha to determine the involute is that this angle is ultimately equal to the pressure angle alpha if the considered point P lies on the pitch circle of the gear and thus corresponds to the pitch point C. As the line of action is formed by the tangent to the base circle, which at the same time runs through the pitch point C, the distance TP is therefore part of the line of action. The involute angle alpha therefore corresponds to the operating pressure angle alpha B. If the point P lies on the reference pitch circle of the gear, the angle obtained is the standard pressure angle alpha 0. So note, the involute angle alpha corresponds to the operating pressure angle alpha B, provided that the considered point P of the involute is located on the operating pitch circle. If point P is on the reference pitch circle, the involute angle corresponds to the standard pressure angle alpha 0. Let us use the involute function to determine the circular tooth thickness S on a circle of diameter d. The figure shows the point P on the corresponding involute. For reasons of symmetry, only half of the tooth thickness is considered. The angle phi shown corresponds to the angle resulting from the involute function explained earlier. However, in order to describe the hatched angular distance of the tooth thickness, we will first use the angle delta shown. This angle delta can be determined relatively easily in radians from the ratio of the circular tooth thickness S half to the radius d half. The angle delta is therefore equal to the ratio of tooth thickness to diameter. Let us now consider the tooth thickness S0 on the reference pitch circle with diameter D0. The same relationship applies to the tooth thickness on this reference pitch circle. The parameters on the reference pitch circle are indicated by the index 0. The angle delta 0 is therefore the ratio of the tooth thickness S0 to the reference pitch circle diameter D0. A relationship can now be established between the two tooth thicknesses S and S0 using the angle gamma marked in red. The angle gamma can be calculated from the difference between the angles delta 0 and delta. Alternatively, the angle gamma can be calculated from the difference between the angles phi and phi 0. The angles delta and delta 0 are expressed by the previously derived relationships. The angles phi are expressed by the previously derived involute function. In this way, we obtain the given equation. We now solve this equation for the circular tooth thickness S and obtain the given formula for calculating the tooth thickness on any circle with diameter d. When applying the derived formula, it should be noted that the tooth thickness S0 on the reference pitch circle depends on a possible profile shift. The relationship between the reference tooth thickness S0 and the profile shift coefficient x has already been derived in the video on profile shift. This relationship is as shown, where m is the module of the gear. While the involute angle alpha 0 for point P0 on the reference pitch circle corresponds to the standard pressure angle of usually 20 degrees or 0.349 radians, the involute angle alpha for point P still has to be determined. To do this, We look at the orange right-angled triangle of point P0 on the reference pitch circle with diameter D0 and the yellow triangle of point P on any circle with diameter D. The angles alpha 0 and alpha shown correspond to the respective involute angles. In both cases, the adjacent side of these involute angles is half the base circle diameter dB. This can now be used to derive a formula for calculating the angle alpha. Let us first look at the orange-colored triangle. The base circle radius dB half is the product of the reference pitch circle radius D0 half and the cosine of the standard pressure angle alpha 0. Let us now look at the yellow triangle. In this, the base circle radius is calculated in the same way, that is, from the product of the radius d half and the cosine of the involute angle alpha. This equation is now solved for the angle alpha. We can therefore calculate the involute angle alpha as indicated from the reference pitch diameter D0, the standard pressure angle alpha 0 and the diameter d on which the tooth thickness is to be determined. Now we have all the parameters we need to determine the circular tooth thickness S on any circle with diameter d. All we need is the reference pitch circle diameter D0, the module m of the gear, the profile shift coefficient x and the standard pressure angle alpha 0. The given relationship of the involute angle will be of importance later. This relationship can be used to determine the involute angle alpha associated with any diameter d from the reference pitch circle diameter D0 and the corresponding standard pressure angle alpha 0. We will later apply this relationship to the operating pitch circle for profile shifted gears, so that in this case the involute angle alpha corresponds to the operating pressure angle alpha b. As already explained in the video on the geometry of involute gears, the reference pitch circle diameter D0 results from the product of the module m and the number of teeth z. It should be noted that this reference pitch circle diameter is independent of any profile shift. This has already been explained in detail in the video on profile shift. However, a profile shift influences the tip and root circle diameter of a gear. The formulas shown apply here, which were derived in detail in the video on profile shift. In the formula for the root diameter, C is the tooth tip clearance, which is approximately 10 to 20% of the module. Using these formulas, we can now determine not only the tooth thickness on any circle with diameter d, but also, for example, the tooth thickness st on the tip circle of the gear. To do this, we must use the tip circle diameter dt as the diameter d in the formulas. This is important because the tooth tip thickness decreases with positive profile shift, and it is then necessary to check that the tooth tip thickness is still sufficient. As a rule of thumb, the tooth tip thickness st should be at least 20% of the module. If this is not the case, the tip circle should be shortened accordingly. For more information, see the video on profile shift. Now let's calculate the circular pitch of a gear. The pitch P is the distance between two teeth. This pitch depends on the diameter being considered. For any given diameter, the pitch P is calculated by dividing the circumference u of the circle by the number z of teeth. If the circumference is expressed as the product of the number pi and the diameter d, the circular pitch is calculated as shown. If we do not consider an arbitrary diameter, but the reference pitch circle diameter d0, we obtain the reference circular pitch p0, which must ultimately be the same for all gears so that they can mesh with each other. The pitch PB of the base circle is also of particular importance. The base pitch is obtained by taking the base circle diameter dB as the basis for the diameter. As explained in detail in the video on the geometry of involute gears, this base pitch corresponds to the distance between the meshing teeth on the line of contact. This base pitch PB is therefore also called the meshing pitch. We can determine the base circle diameter dB using the reference pitch circle diameter D0 and the standard pressure angle alpha 0 as shown. We have already discussed this relationship in detail in the video on the geometry of involute gears. If we use this relationship in the formula for the base pitch, we obtain the equation shown. In this equation we can express the reference pitch diameter as the product of the module and the number of teeth. We can now cancel out the number of teeth and obtain the formula shown for calculating the base pitch. As explained in the video on profile shift, a profile shift has no effect on the reference pitch circle or the base circle. Therefore, the base pitch PB applies equally to all standard and profile shifted gears. The figure shows two profile shifted gears with a profile shift coefficient of x1 equals 0.5 and x2 equals 0.25. The base circle and base pitch are the same as before. In the following, We will determine the operating pressure angle alpha b of two profile-shifted gears as a function of the respective profile shift coefficients. This pressure angle can then be used to determine the center distance. The starting point is the backlash-free meshing of the two gears so that the tooth thickness on the operating pitch circle of one gear fits exactly into the tooth space width on the operating pitch circle of the opposite gear. The sum of the respective tooth thicknesses S1 and S2 is therefore equal to the pitch P on the operating pitch circles of the gears, which must be the same for both, otherwise the teeth could not mesh. We can then use this condition to determine the operating pressure angle alpha b. Note, in this case, the circular pitch on the operating pitch circles should not be confused with a reference circular pitch P0 on the reference pitch circles, since the operating pitch circles are no longer identical to the reference pitch circles for profile-shifted gears. The tooth thicknesses on the operating pitch circles can be calculated using the previously derived formulas. The formulas are simplified in the following. We use the corresponding formula for the tooth thickness S0 on the reference pitch circle. The pitch circle diameter D0 is expressed by the product of the module and the number of teeth. We then obtain the given formula in which we can cancel out the module. Simplifying this equation gives the formula shown. Since in our case the tooth thickness refers to the operating pitch circle, the involute angle corresponds to the operating pressure angle alpha b, as explained at the beginning. We now apply the fact that the sum of the tooth thickness S1 of one gear and the tooth thickness S2 of the opposite gear is equal to the circular pitch on the operating pitch circles. We use the previously derived formula to calculate the tooth thicknesses. The operating pitch circles D1 and D2 can be expressed by the circular pitch P according to the formula above. We can now cancel the circular pitch in the equation we have obtained. We now simplify this equation. We now solve this equation for the operating pressure angle alpha b. Note that this equation cannot be solved directly for the operating pressure angle because the involute function is not an algebraic function and therefore an inverse function cannot be derived. Another possibility, although not very elegant, is to guess the operating pressure angle in several steps to check whether the value obtained from the involute function corresponds to the value calculated from the formula. But there is an approximation formula for determining the operating pressure angle alpha b. The value of the involute function for the operating pressure angle, as determined from the previously derived formula, must be used in this formula. Once the operating pressure angle has been determined by such an approximation method, the operating pitch diameter can be determined. To do this, we have already derived the relationship between diameter and involute angle. Here, D0 is the reference pitch circle diameter and alpha 0 is the standard pressure angle. The diameter d is an arbitrary diameter and alpha is the corresponding involute angle. In our case, since we are looking at the operating pitch circles, the involute angle is equal to the previously calculated operating pressure angle alpha b. We now solve this equation for the operating pitch circle diameter d. The pitch circle D0 is expressed as the product of the module and the number of teeth. This gives the formula shown for determining the operating pitch circle. Note that any profile shift is taken into account by the operating pressure angle. For gears without profile shift, the operating pressure angle is equal to the standard pressure angle, and the operating pitch circles are therefore equal to the reference pitch circles. Once you have determined the operating pitch circles, it is relatively easy to determine the center distance, which is equal to the sum of the operating pitch circle radii. If we use the formula just derived for the operating pitch circle diameters and simplify the equation a little, we obtain the formula shown for calculating the center distance. In practice, however, calculating the center distance using the profile shift coefficients does not make sense in some cases, as the center distance is already predetermined by the gearbox geometry, for example. In these cases, the question then arises as to which profile shift coefficients are to be chosen in order to achieve a given center distance. In these cases, the required operating pressure angle alpha b must first be determined using the formula for the center distance. This is done by solving the equation for the operating pressure angle. This results in the shown formula for determining the operating pressure angle for a given center distance. With this operating pressure angle, the required profile shift coefficients can now be determined from the previously derived formula. This is done by solving the equation for the sum of the profile shift coefficients x1 and x2. This results in the formula shown. If a certain center distance is to be achieved by a profile shift, the sum of the profile shift coefficients must satisfy the derived equation. As long as this equation is satisfied, The coefficients x1 and x2 can be chosen arbitrarily. However, it makes sense to distribute the profile shift coefficients evenly among the individual gears. The sum of the profile shift coefficients should not be significantly greater than 1. This means that the sum of the profile shift coefficients should not exceed the value of the module. It should be noted that gears can also be manufactured with negative profile shift coefficients. If the sum of the profile shift coefficients is 0, the center distance is the same as for uncorrected gears. The operating pressure angle then corresponds to the standard pressure angle alpha 0. In this case, one also speaks of a so-called V0 gearbox. However, if the sum of the profile shift coefficients is greater than 0, the center distance increases and the gearbox is referred to as a V plus gearbox. If the sum is less than 0, the result is a V minus gearbox whose center distance is less than the standard center distance for uncorrected gears. If both profile shift coefficients are 0, which means that both gears are not profile shifted, the result is a zero gearbox. The distribution of profile shift coefficients also depends on how tapered the tooth tips become as a result of the profile shift. As explained in the video on profile shift, the tip thickness should be at least 20% of the module. If this is not the case, the tip circle must be shortened. It may also be necessary to shorten the tip circle because tooth tip clearance changes with profile shift and may no longer be sufficient. As explained in the video on profile shift, tooth tip clearance decreases as the profile shift increases because the teeth taper significantly toward the tip circle and then engage deeper into the opposing gear. As shown earlier, the tip and root diameters of profile shifted gears can be determined using the formulas shown. The clearance C given in the formula for the root diameter refers to the so-called manufacturing tooth tip clearance. The figure shows the rack-shaped reference profile for gear hobbing. The height of this reference profile is twice the module. If only this reference profile were used as the basis for manufacturing the gear, there would be no tooth tip clearance when the gear later meshes with another gear. For this reason, the reference profile is increased by the amount C so that the teeth are rounded more deeply during gear manufacturing, resulting in a tooth tip clearance. This is called the manufacturing clearance C. As long as a gear without profile shift meshes with the manufactured gear, this clearance is also present during meshing. However, the situation is different when a gear with a profile shift is used. In this case, the reduction in tooth tip clearance is clearly visible. So note, the manufacturing tooth tip clearance C given in the formula for the root circle diameter refers only to the clearance between the tool and the gear during gear manufacturing. The actual tooth tip clearance during meshing with another gear is called the operating tooth tip clearance CB. The two clearances are identical only in the case of non-profile shifted gears. The reduction in tip clearance when corrected gears mesh may sometimes require shortening the tip circles to maintain the necessary clearance C during operation. How much the tip circles must be shortened is shown in the following. First, we calculate the tooth tip clearance that results during operation. To do this, let's look at the operating tooth tip clearance CB1 that the teeth of the blue gear 1 have with the tooth root of the red gear 2. The figure shows that the center distance is the sum of the tip radius of the blue gear, the operating tooth tip clearance CB1, and the root radius of the red gear. This equation is now solved for the tip clearance CB1. For the root diameter dr2, we use the previously derived expression. This results in the given formula, with which we can determine the operating clearance CB1. The analogous formula applies to the operating clearance CB2 between the teeth of the red gear 2 and the tooth root of the blue gear 1. Let's take a closer look at the formula for the operating tooth tip clearance CB1. It is immediately apparent from the formula that an increase in the operating tooth tip clearance can be achieved by reducing the tip circle diameter dt1. If this tip diameter is to be adjusted so that the operating clearance CB1 is equal to the manufacturing clearance C, then this equation can be solved for the tip diameter dt1'. This gives the formula shown for calculating the tip circle shortening so that the manufacturing tooth tip clearance can be maintained during operation. The analogous formula applies to the tip diameter dt2' for the other gear. Note that the derived formulas do not depend on the clearance itself. This means that the tooth tip clearance itself does not determine how much the tip circles have to be shortened. A tip circle shortening not only affects the tooth tip clearance, but also the line of contact. The calculation of the length of the line of contact and the resulting contact ratio is described in more detail in the following. As already explained in detail in the video on the meshing of involute gears, the line of action is determined as a tangent to the base circles of the gears. The actual line of contact L begins at the intersection point A between the line of action and the tip circle of the driven gear and ends at the intersection point B between the line of action and the tip circle of the driving gear. As already explained earlier in the video, the distance between two touching teeth on the line of contact corresponds to the base pitch PB. This base pitch can be determined using the formula already derived. For continuous power transmission, a tooth must engage before the currently meshing tooth leaves the line of contact. The line of contact must therefore always be greater than the base pitch. The ratio of the line of contact L to the base pitch PB is called the contact ratio epsilon. The contact ratio must therefore always be greater than 1. The question therefore arises as to how the line of contact L can be determined. This question is discussed in more detail in the following. Let us consider the distance between the tangent points T1 and T2 on the line of action. Starting from point T1, we reach point T2 as follows. Starting from point T1, we first add the distance T1b. Then subtract the distance BA, which corresponds directly to the line of contact L. Now we add the distance AT2 and reach point T2. Therefore, the given equation applies to the distance T1 T2. This equation is now solved for the line of contact L and the formula shown is obtained. In this formula, we must use geometric considerations to determine the individual distances. To do this, let us look at the right-angled triangles drawn. From the yellow triangle, the Pythagorean theorem can be used to establish a relationship between the diameter of the base circle dB1, the diameter of the tip circle dt1, and the distance t1b. This gives the equation shown. This equation is solved for the distance t1b. Analogously, a relationship between the base circle diameter dB2, the tip circle diameter dt2, and the distance t2a can be established from the green right-angled triangle. This equation is now solved for the distance t2a. The last step is to determine the distance t1 t2. To do this, we extend the triangles to form rectangles, as shown in the animation. The distance t1 t2 is the height of the rectangles. Now we look at the diagonal of the large rectangle, which corresponds to the center distance a. In this way we obtain the hatched right-angled triangle. Using Pythagoras' theorem, we can now establish the shown relationship between the distance t1 t2, the sum of the base circle radii dB1/2 and dB2/2, and the center distance a. This equation is now solved for the distance t1 t2. We have now determined all the distances necessary to calculate the length of the line of contact L. Using the terms just derived in the formula, we obtain the equation shown. We can simplify this formula and obtain the formula shown for calculating the length of the line of contact. Note that for the specified tip circle diameters dt, the corresponding shortened tip circles must be used if the tip circle has been shortened. It should also be noted that the base circle diameters of the gears can be determined as indicated using the module m, the number of teeth z, and the standard pressure angle alpha 0. Now all relevant parameters for the mathematical description of involute gears have been derived. In the video description, there is a link to an Excel spreadsheet that can be used to calculate the parameters explained in this video. Note that a possible undercut of gears is not taken into account in the formulas. This leads to a reduction in the length of the line of contact.